All right, let's get started on the next session. That's on Stanford Energy Young Star. Let me introduce the moderator, Professor Alberto Salleo. He is a professor of material science engineering. He's also a department chair. At the same time, he is also innovators working on a variety of problems related to energy. There's probably no better person to get Alberto to chair, to moderate this session. Alberto, please.
Thank you, Yi. Thanks, everyone. It's actually my honor to be able to moderate this session that is focused on Stanford Energy Young Stars. This is a great follow-on to yesterday's Stanford Faculty Innovators. So we have 4 speakers that have past or present affiliations with Stanford. If it's past, it's very recent past. Our first speaker is Fang, currently at the University of Wisconsin. You can come on stage. Thank you. Our second speaker is Yulia Chen, currently at Stanford. Please come on stage. Our third speaker is Jacques de Chalendar, currently also at Stanford. And our fourth speaker is Siobhan Powell, currently at ETH and previously at Stanford. So please come on, and our first presentation will be from Fang.
Hello, everyone. Thanks for coming back, and thanks, Alberto, for the introduction. I'm Fang. I currently just joined University of Wisconsin-Madison, and I was a postdoc at Stanford working with Professor Yi Cui. And for the work I'm going to present today is actually have been done at Stanford. And can I have my slides up? And today I'm going to walk you through our journey, like how to reviving lost battery capacities just using electrochemical method. So the overarching goal of this scientific project is to help decarbonize transportation sectors. So here we are looking at the global CO2 emission breakdowns in terms of different sectors. As we can see here, 73% of the total carbon emission comes from the energy sector. And within this section, 16% comes from transportation sectors. This not only includes aviation and shipping, but also includes the road transportation. As now of today, we have millions of electric vehicles on the road, but we rarely see electric trucks or light purely based on batteries. This is because the energy density of current battery technology is not sufficient to drive those kind of applications. When we talk about the energy density of battery systems, we are talking about within a certain weight or volume, how much electricity can we store. So here on this graph, we are showing the energy density of different battery systems that we developed over the last few decades. So here we have the lead acid batteries, the nickel hydrogen metal hydride batteries, and also the lithium ion batteries that we often use for portable electronics and electric vehicles. But if we want to go beyond lithium ion batteries, we only have one choice. It's lithium metal batteries. Lithium metal batteries, comparing to lithium ion batteries, basically we are only replacing the anode of graphite into metallic lithium. Theoretically speaking, if we can, the energy density of lithium metal anode is 10 times higher comparing to that of graphite. So if we are thinking about energy density in terms of a battery pack, but by just replacing the lithium anode, we can double or even triple the energy density of the whole battery pack. And as you might imagine, everything comes with a price. Lithium metal battery, the electrochemical reactions is much more complicated comparing to graphite. And this is actually a technology that's once commercialized in the 1990s as a primary battery. But people quickly find that this kind of battery is not safe and it cannot really be recharged. And this is partially because of the formation of lithium dendrite. Different comparing to graphite, which is based on lithium intercalation. Between the graphite layers, we have gaps. Lithium ions can go through, go in and go out reversibly. Lithium metal is based on conversion-based reactions. So lithium ion has to be converted into a lithium metal. But instead of forming really flat and uniform thin films of lithium, we often observe is the formation of lithium dendrite, those dendritic structures. But during lithium dissolution process or lithium stripping process, a lot of those lithium dendrites become detached from the current collector. And that has been believed to cause fast capacity degradation or short battery lifetime with this kind of batteries. So we were thinking, is there any way that we can recover this part of capacity just using electrochemical method? This is the fundamental question that we want to ask. So we started our project by looking at the electrochemical potential of inside a battery. So here on the left, we have the cathode, and on the right, we have the anode. The cathode, the electrochemical potential is higher than that of the anode. And at open circuit voltage, when we are not using the battery, there is a flat line in the electrolyte in between them. So no electron is moving. But things start to change when we start to charge the battery. For example, here we are showing the charging process. We are elevating the electrochemical potential of the cathode, where we're lowering that of the anode. By doing so, we are driving the electrons through the external circuit. But at the same time, we are generating an electron potential gradient inside the battery, as shown here. What if at this time we have a lithium filament in this electric field? Will this drive any influence on its behavior? That's the question that we are trying to address here. So here is a simplistic illustration of the scenario that we're imagining. We have the cathode and the anode. We have some isolated lithium that formed during the previous charging and discharging process. It's embedded either within the solid electrolyte interface or in the electrolyte. So during the charging process, we're having an electric field pointing from the cathode to the anode. But lithium is an electron conductor, a very good one. So it will be polarized by this electric field by generating surface charges on its both surfaces. So on one side, it will have a large accumulation of negative charge, and on the other side, it will have an accumulation of positive charge or electron holes. But this kind of accumulation of positive charge or negative charge will disturb the equilibrium state at this interface. For example, the accumulation of negative charge will drive the lithium ions in the electrolyte to be deposited onto this filament. And on the reverse side, the accumulation of positive charge will drive the lithium metal to dissolve into the electrolyte. So the net outcome of this kind of asymmetric deposition and dissolution is a spatial dislocation of this filament toward one of the electrodes. For example, for the case we're seeing here during the charging process, it moves toward the cathode side. And during the reverse process, during discharging, it moves toward the anode side. So this is based on hypothesis. How about can we observe it? So before we designed our own setup device, we look at literature to see what people have been observing for the last 20 or 30 years. So this is work done at the University of Michigan. They're looking at the surface of lithium and the electrolyte during lithium deposition process. You can see the formation of multi-lithium during the deposition process and also its dissolution process. This kind of multi-lithium consists of thousands of lithium filament. And we are seeing it under optical microscope. As you can see here, it's really hard to tell which filament is connected and which filament is not. And it's even harder or nearly impossible to see whether if they have any kind of movement. That's why, for the last 30 years, we have formed this consensus that once those isolated lithium become detached from the surface of the electrode, this part of capacity is permanently lost. And we also gave it the name called dilithium. So instead of using a two-electrode structure, we actually designed our own device with a third electrode in between them. We patterned a copper strip as the island between two electrodes, lithium and NMC cathode, and then we electrochemically deposit lithium metal on it to serve as a lithium island. So this is what we observe. Before we cycle the battery lithium is homogeneously distributed on this island. But after a 3-hour charging process, one side of this lithium completely dissolved, leaving the black residue here is called solid electrolyte interface. And on the other side, we are observing a large amount of lithium deposit onto this island. So this phenomenon is consistent with our previous analysis, that one side is dissolving, the other side is depositing. So if we put those phenomena that we observed together, it's like if we are using the same kind of current density during charging and discharging, this lithium filament will move back and forth between two electrodes until it's completely consumed during this process. But our opportunity also lies in this phenomenon, because this kind of movement, the rate of it, is dependent on the current density. So what we're trying to see is it possible that we can somehow manipulate the behavior of the filament to help it move toward the anode side to reestablish this electrical connection, to recover this particle capacity. So this is one of the demonstration experiments that we did with half cells. Half cells is based on copper and lithium to eliminate the influence of the cathode part. Basically, the performance that we're looking at is on the copper side. So during this experiment, during the first cycle, we want to form a certain amount of dead lithium or isolated lithium on the copper electrode. And during the second cycle, we want to see whether we can recover it. So during the first cycle, we are forming 0.37 milliamp per hour per square centimeter isolated lithium on the copper electrode. And during the second cycle, we still want to do deposition, means we are charging the battery. Now we are gradually lowering the cell voltage of the electrochemical potential of copper to deposit a certain amount of lithium, fresh lithium, onto the substrate. And then we start to dissolute, we start to strip it away from using electrochemical method. But during this time, we are not only stripping away the fresh lithium we just deposited, we are also promoting the growth of isolated lithium toward the copper substrate. So that's why we're seeing actually over 100% Coulombic efficiency in this case. Coulombic efficiency is the ratio between delivered capacity versus stored capacity. That means that the previous inactive capacity is actually being reactivated during the second cycle. If without isolated lithium presence, the Coulombic efficiency of the batteries is usually about 92 to 93%. And the difference between those two cells is the capacity that we generated during this cycle. So this is a very, very newly discovered electrochemical phenomenon. What else can we, how can we use this kind of phenomenon in real applications? Here I want to give you 3 examples. The first one is lithium metal batteries, where we actually studied it. To utilize this kind of fundamental research, we developed a new charging protocol to implement this understanding. Not only we want to charge the battery, but we also want to implement a short, fast discharging step to recover the previous lost capacity. By doing so, during every cycle, we're using about 4% of battery capacity, but in the long run, we're extending the battery lifetime by 30%. Another example is fast charging of lithium-ion batteries. This is one of the major concerns from customers that is hesitant to purchase in electric vehicles. During this fast charging process, isolated lithium also forms on graphite electrode. But by using this kind of activation protocol, we can also dramatically extend the lifetime of lithium-ion batteries even after the fast charging process. Another potential application would be to regenerate or recycle used batteries. This can become extremely important after a few years when we have a large amount of battery retired from transportation. What if before recycle them, just draw out the raw materials from the batteries? Can we give them a second life just using electrochemical method? And that's something we think can be highly promising. With that, I would like to thank my advisor, Yicui, and the group for support, and also our funding agency from DOE and Battery 500. And thank you all for your time and attention. Thanks.
Thank you, Fang.
Hi, my name is Chen, or Yulia Chen. I'm with the Energy Science Engineering Department of Stanford University. I'm currently a PhD. And today I would like to talk to you about quantifying regional methane emissions from oil and gas operations with aerial surveys. So why do we care about emissions from oil and gas? I'm saying this not because ExxonMobil is the founder of this event, but because IPCC also agrees so that natural gas will continue to be used for decades. And this is the primary energy projection under the 1.5 degrees C most stringent mitigation scenario and averaged across 6 different mitigation pathway models, all saying that although the future is clearly going to be dominated by, well, wind and solar and renewables, natural gas will continue to be used for decades. Therefore, it is important that now that we are still using and producing this much natural gas, how can we limit the climate impact of producing them? What is the climate impact of producing natural gas? In 2010, the IPCC estimate for global anthropogenic greenhouse gas emissions is about 50 gigaton of CO2 equivalent. Although CO2 contributes the most of it, methane, or CH4 here, also contributes a significant 16%. And about 1/10 of that global CH4 emissions are from the US. And the US EPA, Environmental Protection Agency, estimated that about 32% of the US methane emissions are from the oil and gas sector. So if we apply this share of methane emissions from oil and gas globally, this can easily become a gigaton challenge in terms of CO2 equivalent. Actually, to say that this is a gigaton challenge is an understatement for at least 2 reasons. Number one, this chart here converts the CH4 into CO2 equivalent, assuming methane's global warming potential of 100 years at about 30. However, due to the relatively shorter lifetime of methane in the atmosphere, curbing methane emissions can have more immediate climate benefits. If we apply a 20-year methane's global warming potential of over 80, then the climate impacts of methane here will increase by 3-fold. And the other reason for an underestimate is that we know for a fact that this number that's estimated by EPA is an underestimate. And how much methane is actually emitted from the US gas supply chain? In 2015, the EPA Greenhouse Gas Inventory, or GHGI, estimated 8 megaton of methane that's estimated from the oil and gas sector. For the same year, Everest et al. Compiled more recent studies, and they generated an estimate which is widely accepted in the academia, saying that actually more than 60% than the EPA estimate, or 13 megaton in total, is emitted from the system. However, more recently, what we have found is that there are many more super emitters, as is shown in this infrared footage that's done by Jeff and Evan of our group, showing that these abnormal and super emitting events of the sizes of tons per hour, or even tens or hundreds of tons per hour, is actually more often than we expected. So although these things are rare, but because of their huge sizes, they can contribute disproportionately to total emissions. And if we take into account these abnormal superemitters, we know that the actual total emissions from oil and gas and methane emissions will actually be higher. But the question is, higher by how much? Luckily, we already have the technology to answer this question. Kairos Aerospace, which is a company that's based in Mountain View, California, has this hyperspectral sensor that is capable of making the invisible methane visible, as is shown in this example here. And more importantly, because Kairos Aerospace is an airplane-based sensing technology, they are capable of surveying a really extensive area of oil and gas facilities within a relatively short time. So this detection speed is essential for collecting a really large sample. And a large sample is important because we are interested in detecting and understanding these infrequent super-emitting events. So we here as the Stanford team, the Environmental Assessment and Optimization Group led by Professor Adam Brandt, we verified the quantification performances of their technology via single blind controlled releases of methane. So we on the ground releases these compressed natural gas from the tanks, and they on the airplane measured it and reported to us what they found. So what we found is that the technology works great. The slope here is close to 1, and the spread here is expected considering how difficult and how unpredictable it is to predict the hyperlocalized wind speed. So Kairos Aerospace repeatedly visited the oil and gas facilities in the New Mexico Permian Basin. The Permian Basin is now the largest and fastest growing oil and gas producing basin in the US. And the way that they sample this area is like this. They will firstly fly to the predetermined polygon and cover a stripe of it and turn the flight around to cover a partially overlapping stripe of it. And they will do this over and over again until the entire polygon is covered in a long molding fashion. So within just 115 flight days in October 2018 to January 2020, Kairos was able to cover over 90% of the facilities in this area, which encompasses over 30,000 wells and over 15,000 kilometers of pipelines. And the color here on this map indicates the number of visits to these individual wells. So on average, each wells in this area were visited 4 times. Not only is this a comprehensive survey, this is also a repeated comprehensive survey, which has never been done before. What we found was the data of this survey is quite astonishing. In total, we quantified 153 tons of directly measured emissions in this area. And we also measure the total emissions, which also takes into account emissions which are below Kairos detection threshold, and also from the assets that were not covered by Kairos in this area. And 194 tons per hour of methane corresponds to 9.4% of the gas production here, which is much worse than the EPA's GHGI estimate of just 30 tons per hour. And the 30 tons per hour is even after we take into account the production growth in this area recently. And what's also interesting to point out here is that the top 12% of the sources that's detected by Kairos account for about half of directly measured emissions. Now, this is actually good news and bad news. It's bad news because we know that EPA misses these infrequent events, but these infrequent events, the top 12%, are actually what matters and what drives the total emissions. And this is good news because we know that once we handle these handful of fuel, these fuel super-emitting events, we can get halfway there about emission mitigation. So to conclude, we know that limiting the climate impacts of producing natural gas is necessary in a world of continued gas consumption. And aerial surveys, unfortunately, has unveiled a leakier system, at least in New Mexico Permian Basin in 2019. The entire situation is quite concerning. Some producers are better than others, but overall, the actual methane emissions from oil and gas can be times higher than the EPA estimate. And we also found that the aerially detectable super-emitters account for the vast majority of total emissions. And what that tells us is that we want to build a global methane monitoring system, then we need to have more of these remote sensing technologies in place. And our group here at Stanford is testing a series of remote sensing technologies via single blind control releases of gas right now. Actually, as I'm talking right now, my fellow PhD students and postdocs are in the desert in Arizona and playing with release apparatus and sandstorms, actually, to having all these technologies tested and being deployed. And thank you for listening.
Thank you, Yulia. Our next speaker is Jacques de Chalendar, also currently at Stanford.
Thank you. Thanks. Decarbonizing electricity and electrifying heating and cooling and light transportation will probably get us about halfway there towards net zero. But this also means that the electric grid, both on the supply side and on the demand side, will have to change very fast. The map that you see behind me summarizes some recent research to track hourly emissions through the US electricity system, from production to consumption while accounting for exchanges. The electric grid is one giant interconnected machine. So what we do on one side of the grid affects another. Decarbonizing electricity means injecting large shares of intermittent renewables at the transmission level. So in the future electric grid, flexibility will have tremendous value. More than that will be needed to achieve our electrification and decarbonization targets. So today I'd like to talk about some evidence we found that there's already significant amounts of flexibility in the grid. My case study is the campus on which we are today, whose electricity consumption is roughly equivalent to a 30,000 people city in California. This is our living lab. And this is my rough schematic for our integrated energy system. So we have what's called a district energy system on this campus. We produce the heating and cooling centrally at the energy plant on the bottom right in the form of hot water and chilled water that's then sent through a network of pipes to the 130 roughly buildings on campus. And the system is almost fully electrified because we use mostly electric heat pumps to produce the heating and cooling. The first source of flexibility I'd like to explore is in scheduling the machines in that central energy plant. So first, a real-world experiment. In the summer of 2018, we participated in a demand response program with our utility, with roughly 5 megawatt bids, which roughly corresponds to a third of the energy facility's electricity consumption, which is shown as a green line on the bottom left. The orange line here, the second one, is the electricity consumption of the buildings. That's what we don't control, our inflexible load. And the blue line is what PG&E, what our utility sees. That's our total electricity consumption. The flexibility for responding to these events was mostly coming from the thermal energy storage tanks, big insulated steel tanks with water that you see on the right. And we also developed prototype software tools to help us schedule the facility and respond to these events. So here you can see we successfully responded to 3 events that were called by the utility. A second experiment is a thought experiment where I'm using the same hourly scheduling tools to consider 2 what-if scenarios. In these heat maps, every column in the images corresponds to a day of the year, and every row to an hour of the day. In the top one, and both of them are showing Stanford's hourly total electricity consumption for a year. In the top one, this is the optimal behavior under our current electricity tariff, which is telling us to have a consumption that's as flat as possible and then to consume less in the early evening hours that are typically more expensive. The bottom one assumes that we're paying a price on carbon that's so high that we basically just want to shift as much of our load as possible to the middle of the day because this is California. And so you see that load drops to lows of 20 megawatts in the middle of the day, in the middle of the night, and 45 megawatts in the middle of the day. So next, I'd like to talk about some options that are available today, but really will be more available tomorrow given investment. And the black box I'd like to open next is the energy consumption of the buildings, and specifically cooling, that so far I've assumed is inflexible, just something that I have to respond to. So this is going to change the decision-making problem that the district energy system operator is facing, because now I can call on thermal demand response. And so this is going to introduce new cost functions, decision variables, and operating constraints for each of the 130 buildings on campus. So it's going to complicate my problem. The buildings that I'm considering are what are called commercial buildings. So the cooling comes in the form of chilled water that's used to cool down air, which is then sent to the different thermal zones in the building. The weather, occupancy, building control systems, physical characteristics all interact to determine the building's cooling load, which is why answering this question is not as easy as it seems. If I increase the temperature set points in a subset of the zones by 2 degrees Fahrenheit, how much does the cooling load drop? So we went out and started testing some buildings. Here I'm showing some data for a building on the engineering quad. The y-axis corresponds to daily cooling load, and the x-axis to the mean daily temperature measured at our Stanford weather station. So each dot is 1 day's worth of data. The blue dots correspond to our low temperature set point, 74, and the red dots 2 degrees higher. So the difference between the two curves here is our estimated flexibility for this building, 20%. We tested multiple buildings on campus, 3 in 2020, 6 in 2021, 11 just this summer. But testing all 130 buildings on campus is going to be very costly. At that point, we've implemented the program. So we also have developed methods to extrapolate results from the buildings that we tested to untested buildings to estimate campus-wide impacts. And so the plot that you see here shows what's called a low duration curve, and here it's a low duration curve for chilled water. So I'm looking at each of the different days of cooling demand for the campus and ranking them from highest to lowest, left to right. And the blue curve is our business as usual. The orange curve here is what we think we can do with 10 days of demand response. So one important takeaway here is that this would lower our capacity requirements for infrastructure by 14%. So that's where the big savings are. So one last question I'd like to touch on that we're just really starting with: what are the costs to occupants? So earlier in the summer, there was a power outage that I think some people have mentioned already, and I was on campus at a conference just like this one. When there was this power outage, it got very hot in that room because it was hot outside. So the following day, we sent a survey to the participants to ask them about their willingness to accept cooling load service interruptions similar to what we had just experienced, assuming it would lead to lower energy costs and environmental benefits for the campus. And a few interesting things came out of the 21 responses that we got. First, there was a lot of support for the program. That maybe not so unexpected. Second, the support drops if you call on the service more often. And third, most interesting to me, there's a big difference depending on if you call on the service the day of versus the day before. And so finally, I'll leave you with these 3 messages. The electric grid is changing, so we're going to need flexibility. There's already a lot of flexibility in the system today, and given investment, much more flexibility can be available tomorrow. Thanks.
Thank you, Jacques. So before we give the floor to our last speaker, I want to remind you can ask questions through your mobile app, and then we'll have a Q&A session at the end of this last talk. Last but not least, Siobhan Powell, currently at ETH, just recently from Stanford.
That's right. Thank you so much for the invitation. Yes, I just graduated with my PhD from here, working with Professor Rajagopal, Professor Azevedo, who you heard from a little bit about this work yesterday. Today I get to go into more detail. The work that we did was all about co-optimizing the EV and grid transitions. So both the transportation sector and the electricity sector are undergoing these rapid transformations, and they're coupled together by EV charging. This charging can cause problems, maybe by accelerating aging of grid equipment or increasing electricity prices, but it can also work better, and we really wanted to focus on understanding this coupling and finding ways to improve it so that the transitions help each other. First, understanding it, I'll break it down into 3 sort of factors that describe charging demand. And the first is behavior. So if you think about your mobility patterns today, people might drop a kid off at school, go to work, run an errand. Everyone has a different pattern, different needs. And on top of that, different preferences. Most people don't need to charge every day when they have an EV, and so they get to choose how frequently they like to charge, when and where they like to charge. So this is something that we started to study. The second factor that's very related is about charging infrastructure. So if this person has a charger at their home or at their workplace, then they have the option to charge there. If they don't, they have to pick from other options. This has a very big impact on their charging demand profile and what they do to the grid. And the third is what we sort of traditionally think of as charging control. So once someone has decided to plug in somewhere, within the time that they're plugged in, you could delay when they receive their energy or reshape the profile of how they receive that energy to, for example, reduce their electricity bill. Fortunately, there's a lot of flexibility in charging, so each of these things can be changed with different policy levers. The first might be by changing prices or increasing battery range. So if someone has a longer range, they might make it an extra day before they choose to charge. Or if we give more access to workplace charging, someone might decide to shift their charging to the middle of the day. Or if we change pricing signals, that could also change how this automated control is done. And so in the study I'll talk about today, we looked mostly at these second two features and designed scenarios to understand how they can improve the grid impact of charging in the Western US. We started with a very large data set of charging for the Bay Area and dove into that to understand charging behavior, especially interaction with charging infrastructure. We have several scenarios. Okay, So this first row of scenarios was all about charging infrastructure. So the first one, what if everyone has access to home charging? You see we have a big peak of demand in the evening. And then all the way to what if there's low access to home charging and a lot of charging is covered by public charging stations. And you see you get a big peak in the middle of the day. We also looked at scenarios of control. So at single-family homes, the most common rate schedule would have a low price period starting in the evening, maybe at 9 p.m., at 11 p.m., at midnight. And about 30% of the drivers in our data set timers to delay their charging to start until then. So this example here has a 9 p.m. start time. Or at workplaces, maybe you have a demand charge, which encourages workplace charging to be flattened throughout the day. So these different scenarios, we modeled charging demand under each scenario for every county in the Western US, in WEC, the US region of WEC, for 2035. And then we combined that with an economic grid dispatch model to look at the generating resources we'll have in 2035. We'll have more wind and solar. We'll have a different fleet of coal and gas generators. And when you put these charging scenarios in, what happens to the grid? So I can only look at a couple of quick results. The first is about peak demand, sorry. So the gray in these figures is baseline demand, so consumption not from electric vehicles, from everything else that uses electricity. And you can see that it's highest in the evening. So scenarios where we add a lot of charging in the evening have a high evening peak. Scenarios where we add daytime charging actually create a new peak in the morning that's higher even than the evening peak. But total demand is not really the driver of the impacts that we looked at. When you look at net demand, which is what's left once you take away the contribution of non-fossil fuel generators, you have this big dip in the middle of the day because there's a lot of solar in 2035. And so we see in total demand, we had some cases with morning peaks. In net demand, all the peaks are in the evening, and the highest peaks are from the scenarios with evening charging. In some days of the year, there's not enough capacity to cover those high evening peaks. And so we looked at how much grid storage you'd need to add to shift around generation and cover those peaks. As you increase the number of EVs on the road, this amount of storage needed increases as well, but not evenly across scenarios. So the scenarios with universal home charging, high home charging access, you needed more storage to cover those peaks. And the scenarios here on the right, with lots of daytime charging, you needed less storage to cover those peaks. We also found that's a 56% reduction by switching from the universal home case to these low home charging cases. We also looked at control, so that 9 p.m. timer I talked about was particularly bad because it creates a really big spike in the evening. The workplace charging we looked at spreads a lot of charging demand through the day towards that crunch period in the late afternoon, early evening, so that also increased the demand for storage. And finally, I'll talk a little bit about emissions. So this is operating emissions. This is grams of CO2 per mile traveled. On the left first, this is the base case grid we looked at for 2035, and you can see the two daytime charging scenarios have the lowest emissions per mile. And as you increase the amount of home charging used, emissions increase as well. It's about a 5% difference between the worst and the best case. But we tested a sensitivity where you had more renewables in the grid by 2035. And there the difference grows. So as we have more and more renewables, charging during the day becomes more important in the Western US. This was the really big conclusion of our study, which, by the way, is listed at the bottom, available open access. You can go and read it and find all the details there. But the big conclusion was that daytime charging infrastructure, having more daytime charging improved every measure of grid impact that we studied. So this is a really important conclusion for policymakers looking to invest and build all the thousands of charging stations we need to put in before 2035. The more daytime charging infrastructure, the easier this will be for the grid. We also looked at control, and it's made a much smaller difference than changing charging infrastructure. So There's a lot of work left to do. We're looking at doing this for other regions, maybe countries in Europe, maybe other parts of the US, looking at designing rates so that the controls work better, looking at how this affects grid planning. So if you're interested, would like to talk, would like to get involved, please don't hesitate to contact me. Thank you.
Thank you, Siobhan. And thank you to all the speakers for really great talks. So now it's time for questions. Thank you from audience members who asked questions. The first question is for Yulia, and it has to do with the fact that the methane emission in the Permian Basin is a lot higher, than what estimated. What do you think this looks like at the global level, considering maybe similar types of leakages?
Thank you for the question. I'd like to share with you 2 additional pieces of information. When we first published this article regarding the methane emissions in New Mexico, we got a lot of shouting emails. No, this is not true. This cannot be true. And I would like to make some clarification that our conclusion for now only applies to the New Mexico part of the Permian in 2019. New Mexico, unlike Texas, which is also has Permian in its part, has never seen this much of oil and gas production before. And back in 2019, when we did the survey, the New Mexico state government was only ramping up their regulations on flaring and venting to cope with this oil and gas production levels. We do believe that the superemitter phenomenon and that the underestimate is true and probably applies more generally in the US and globally. However, the New Mexico Permian case is probably one of the more extreme cases of overestimation, of underestimation by the EPA GHGI. And the second piece of information that I would like to share with you is that, so I can't really tell you how this is going to imply about global methane emissions, but there have been satellites to monitor global methane emissions, but those satellites have pretty coarse resolution, so they can only detect the really large emitters that are over 10 tons per hour. But these are actually the ones that matters the most because their disproportionate size drives total emissions. And unfortunately, by 1 year of daily monitoring, so there's a satellite called Tripomi that overlooks the globe and daily, finds that there are many, many more ultra emitters. We term this as ultra emitters. They are bigger than the super emitter than we expected. So that's actually says something that's really bad about global methane emissions from the oil and gas sector. But fortunately, there are many companies working on this. There will be many more airplanes and satellites that are to be launched in the coming years or so, and we will have a much better monitoring systems globally and have very frequent revisits to all of the sites to be able to share this information.
Thank you, Yulia. The next question is for Fang, and it is, where do you expect your battery technology to go, and what potential improvements do you think can happen?
This can be a really big question for me as an early career faculty member. Today I only showcase one of the studies that we did to improve the battery safety and to better understand how battery works. But there are thousands of really good work in this field trying to improve the durability and the safety of batteries for a number of applications. So I think we share the same dream. We want to offer the technology that can potentially provide affordable and robust electricity for everyone on this planet. And this definitely takes more than academia and also industry and governors to make this happen. But for us, like scientists and engineers, we want to make the technology available for us to choose from for different applications. And that's my thought on this. Yeah.
Thank you, Fang. Really, it's really a good thought that it takes a whole ecosystem to drive impact. The next question is for Siobhan, I believe, and it has to do with public chargers versus home chargers. What do you think drives a difference in cost between the two, and what can be done about it?
It's a great question. I think there's a long way to go in terms of having enough public chargers. Some things that contribute to the cost are installing them, installation costs, figuring out the grid connection. I think putting in a home charger can be much easier, but there are also government subsidies that help both types. There could be more support for public charging. One thing I'd like to say is I think it's really important to get this right. In California, so far we've had early adopters driving EVs who mostly have single-family homes, can afford to put in home chargers. The California Energy Commission did a really interesting survey earlier this year and found more than 50% of residents of California won't have easy access to home charging. And so when we want to get to deep adoption past 50%, towards 100%, we need to figure out other options. And so it's very serendipitous that it's also good for the grid, but I think working on public charging and solving this problem will be really important. But there are a lot of different pieces that make it expensive, so there's a lot of work to be done.
Thank you, Yulia. Sorry, Siobhan. We have now one question for Jacques. Essentially, how representative is the Stanford campus? We have pretty special weather here. So your study is focused on Stanford. How representative is it? And would you have the opportunity to find a campus somewhere else with different weather conditions and experiment with that?
So for the first question, so on whether I've thought about sort of other places and winter weather. So there's one question about the winter versus the summer. Maybe I'll take the next one, which was humidity versus Stanford's climate, which is very mild. So actually, I'm lucky. I was able to see some data just this summer from a corporate campus in New England, where there's a lot more humidity. And actually, it was surprising, but the results were pretty similar to what we got here with similar. And so it's just some preliminary data, and we're just getting started. And I guess to answer the second question, yes, we'd really like to start doing similar experiments elsewhere. And there are at least a couple places I've started talking to. And actually, this is maybe a good time, if you're at a university or if you have a corporate campus and you'd like to talk about doing these experiments, I'd love to talk about that. Maybe just one more thing. On one of the previous panels, there was someone mentioned something about innovation versus deployment. The technologies I'm talking about here are really commercially available. One of the things, though, but they're not being used. Flexibility is not being used, not on a massive scale. So there's a lot of work to be done on the R&D side, thinking about how to reduce those barriers to adoption and show how to do things in a scalable way. And that means running experiments like these here and elsewhere.
Thanks, Jacques. Well, what type of data would you need to run an experiment elsewhere?
So there's data collecting, and there's also controls. So actually, a lot of work has already been done collecting data and looking at data in buildings. In our case, we're lucky we have pretty granular data, as in I'm looking at the temperature, airflow rates in all of the different rooms. So right now, something like 1,500 rooms on this campus. But I also control the temperature set points in those rooms. So I control certain building energy management system parameters. But the experiment I was just talking about, the one this summer on another corporate campus, they had much more limited data, and there's still things you can do.
All right, thanks. Well, we have come to the end of this session. There is many more questions, but you probably know how to reach our speakers if you have questions. Let's thank our speakers again, our young Stanford Energy stars.